Large language models use retrieved information to provide more accurate answers, and that helps reduce hallucinations. BuzzRobot guest today, Bowen Jin from the University of Illinois Urbana-Champaign, shares different methods on how more efficiently use retrieved information for long-context LLMs.
Hi everyone, I'm Bowen. I'm a fourth-year PhD student in UIUC, and today I'm very glad to talk about our recent work called Long-context LLMs meet RAG, overcoming challenges for long inputs in RAG. So this work is done during my internship in Google. It's under a collaboration between Google and UIUC. First, let's come to the motivation of this work. So we know that RAG supports various applications. So the thing is, large language models often struggle with factual inaccuracies and produce hallucinated content when faced with knowledge-intensive questions. For example, if we just directly ask LLM a chemistry domain question, it may not be able to answer it correctly. But what RAG proposes is that we can just have LLM have the ability to interact with a chemistry knowledge base or chemistry external corpus. Through retrieval, we can find out some relevant information for the given query, and we can just concatenate the retrieved information together with the query and input them together into the LLM. And by doing this, LLM will be given not only the query, but also some potentially relevant information from the domain external knowledge corpus. So this is what RAG is doing. And at the same time, large language models nowadays are able to support longer contexts because of the advance in compute and research on efficient training. We know that originally GPT-3 only support 2,000 max token lengths. I think Llama 1 only support it also only support 2,000 max token lengths, and Llama 2 support 4,000 max token lengths, and Llama 3 support 8,000 max token lengths, and even Llama 3.1 now support 128,000. So we can see the trend of the very fast increasing of the expansion of the LLM input token lengths. And nowadays, the best LLM with the longest max token window is Gemini 1.5 Pro, which can support about 2 million input tokens. Given that long context LLMs nowadays supports such very big long input, and it seems like they have quite some capability in processing those long input, then many people start to argue that if we still need RAG in the long context LLM scenario. So the point is, what RAG is doing is it will do some retrieval on the domain knowledge base, and then feed the retrieved information, which are some potentially relevant information together with the query into LLM. So if we have a super powerful long context LLM, we may just remove the retrieval part. We can just feed all those domain information into the long context LLM together with the query. And if the long context LLM have the very good capability to processing long input, it should be able to figure out the very useful information from the very long, the whole domain corpus. And it's kind of assuming that long context LLM will just replace the retrieval. It would do the retrieval itself and then do the cross answering or reasoning. So people are arguing that previously we are using RAG with short context LLMs. We usually retrieve top 1, top 3, top 5 documents, and then feed them into the short context LLM for RAG applications. Now we have a long context LLM. Can we just remove the RAG part, just remove the retrieval part, and directly use the long context LLM for the whole domain corpus understanding? So it's like a transition from this to this. However, there is actually a middle step between totally transferring from RAG with short context LLM to long context LLM only. So it's like, what if we replace the short context LLM with a long context LLM in RAG? So we still do retrieval, but we increase the number of retrieved documents in RAG with a long context LLM. So if we have a long context LLM, we can take multiple, we can have 100 retrieved documents input as context, or even thousands of retrieved documents. What will the RAG performance be like if we increase the number of retrieved documents? So the RAG with long context LLM can be served as a middle step between we transfer from RAG with short-term LLM to a long context LLM only. And this RAG with long context LLM is the focus of our work. The point is that if we adopt a long context LLM in RAG, we are able to increase the number of retrieved documents. And if we increase the number of retrieved documents, we'll potentially improve the retrieval recall. And this means that we will have more relevant documents put in context for the LLM. However, existing works in RAG, they usually just adopt top 1, top 3, or top 5 retrieved documents and leave this study of long-context LLM in RAG and explore. When studying this long-context LLM in RAG, we try to conduct the analysis with several analysis steps. For each analysis step, we'll have one research question. For this page, this is our first research question, which is, does a larger volume of retrieved context consistently translate to better performance when using long-context LLM in RAG? So it's like if we increase the number of retrieved documents in RAG, and if we can have a consistently better performance. So we conduct experiments on natural question dataset, and we also show the result of PopQA in our paper appendix. And we try two kind of retriever, E5 retriever and BM25 retriever. And we have experience on 4 generators for large language models: Gemma 7 billion chat, Gemma 2 9 billion chat, Mr. Namo, and Gemma 1.5 Pro. Very straightforward intuition is that if we increase the number of retrieved documents, we'll have higher recall, and which means that we'll have more potentially relevant documents retrieved in context. And if a long-context LLM have a very strong long-context processing capability, we should have a continuously increasing RAG accuracy. However, this is actually not the case. We can see that in our 2 figures. The left one corresponds to using E5 as a retriever, and the right one corresponds to using BM25 as a retriever. So in both figures, we see that for most LLMs, the RAG performance actually have increase and then decrease phenomenon. It's not continuously increasing. And also, if we look at a background is that E5 is a strong retriever than BM25 in natural question dataset. So if we look at comparing this 2 sub-figures, we can see that if we use E5 as a retriever, the RAG performance increase very quickly and reach the peak very quickly, and then start to have a very sharp decrease. But if we use BM25, which is a much weaker retriever, the performance usually is continuously increasing, and then only have a very small decrease at the end. So why this happens? So the observation is that with a strong retriever across all LLMs, increasing the number of retrieved passages initially improves performance, but then leads to a sharp decline. But the outlier is Gemini 1.5 Pro. So we'll talk why this happens in the later slides. If we use a weak retriever, which is BM25, the performance generally exhibits a continuous increase or a slight decrease as the number of retrieved passages increases. The first insight is that the effectiveness of increasing retrieved context size in RAG depends on the strength of the retriever. So if you have a strong retriever, the RAG performance will have a very sharp inverse U-curve pattern. But if you have a very weak retriever, it seems to be more consistent and only have a very slight performance decrease. And since this kind of increase and then decrease curve is kind of counterintuitive, it's not aligned with our preliminary thinking about increasing retrieved number of documents will have high recall, more potentially relevant documents. It's not aligned with this. So this suggests that some other factors beyond simply the amount of retrieved information or relevant information are at play. So our second exploration is with this kind of research question: do the observed performance bottleneck or do the observed increase and then decrease RAG performance curve originate from limitations in retriever's capability to identify relevant information, or from the long-context LLM's capability to effectively utilize the retrieved context? So in this experiment, we dig into detail into the analysis of the retriever. We will show the recall and precision of different retrievers. We adopt 2 retrievers in this experiment, E5 and BM25. So E5 is shown on the result of E5 is shown on the left, and the result of the BM25 is shown on the right. And for both experiments, we are using Llama 3 8 billion chat as the LLM generator. And we print out the recall and precision of the retriever. So what recall corresponds is it's just measuring if relevant document appears in the retrieved documents. So for one query, if it can successfully retrieve at least one document which is relevant within the top K retrieved documents, we'll give recall at K to be 1 for this query, and the total recall at K is calculated as the average of all the query level recall at K. And precision at K is trying to measure how much noise exists in the context. So it's like the ratio. Precision is the ratio of the relevant documents inside all the total retrieved documents. So we can see that the higher the precision is, the less noise we have in the context, and the lower the precision is, it means that we have more irrelevant or hard negatives in the context. So if we look at these two figures, we can have some observations. We can first look at the left subfigure, which corresponding to using E5 as a retriever. The green curve and the red curve correspond to recall and precision, respectively. And the value for the recall and precision can be seen as the right y-axis. And this blue curve corresponds to the final accuracy. And the value of this can be referred on the left y-axis. One observation is that if we compare RAG accuracy and recall, we can see that for every number of retrieved passage data point, actually the RAG accuracy value is always lower than the recall value. So why this happens? So if we have recall equal to 0.8, this means that 80% of the queries will have a relevant document retrieved in context, but still we will have a less than 80% RAG accuracy, which means that at least for some queries which have the relevant document retrieved, the LLM still cannot answer it correctly. So this kind of means that the noise matters. So even though we can retrieve the relevant documents in context, there is still some irrelevant documents or negatives retrieved. And maybe the LLMs are misled by those noise. And even though we present the relevant documents in context, still cannot answer it very correctly. And the second finding is, okay, if we think that noise is very important, how can we measure the noise? Precision seems to be a very straightforward thinking to measure noise. And the higher the precision is, the less the noise is presented in the context. But if we compare this subfigure 1A and subfigure B, we can see that actually E5 retriever have a higher precision than the BM25 retriever. But if we look at the RAG accuracy, if we do RAG with E5, the RAG accuracy decreasing is more sharp than the RAG performance decreasing with the BM25 retriever. So this means that actually precision itself or precision alone is not a very accurate measurement of how much noise or how's the strength of the noise present in the retrieved context. In the second analysis, we'll dig into details of how to measure the strength of the negatives and to analysis what other factors is correlated to the strength of the noise. Okay, so for this second analysis question, we would like to provide two kind of insights. So the first one is the influence of irrelevant passages. So we can see that for both E5 retriever and BM25 retriever in RAG, even though we can present the relevant documents in context, in many cases, the LLM can still not be able to accurately answer this question. So they are kind of like misled by the negatives or irrelevant documents retrieved in context. And the second insight is the limitations of precision as a matrix. As we just mentioned, if we use E5, the precision is higher than using BM25 as a retriever. So, but if we use E5, RAG accuracy will have a sharp decrease than the decrease of the using BM25. So it means that precision alone is not a very good metric for measuring the effect of the noise. In the third part, we try to have a deeper understanding of hard negatives and propose two kinds of research questions. The first one is, how robust are current long-context LLMs to these hard negatives? And the second one is, does the impact of hard negatives vary with the retriever use? Actually, we conducted a synthetic experiment here, which is kind of different from real-world RAG scenarios. So our setting is that we'll put one golden document plus multiple negatives from different retrievers in context, and input this as a kind of pseudo retrieve context together with a query into the LLM, and let the LLM to answer the given query. And we test four kind of retrievers or four kind of negatives from different retrievers. The first retriever is just random retriever. The second one is BM25, third one retriever, fourth one is E5. And we try three kind of LLM generators: Gemma 2, Mr. Nemo, and Gemma 1.5 Pro. We would like to show the capability of different retrievers on the left subfigure. So the y-axis corresponds to the precision of the retrieval, and the x-axis corresponds to the recall of the retrieval. So the more the curve is on the upper right side, the better the retriever is. So we can see that in the natural question dataset, E5 is the best retriever, and the contriever is second best, and BM25 is the third performed retriever. Okay, then on the left three sub-figures, we would like to show the performance of how the different LLMs perform with the number of increased hard negatives or the increased like the misleading documents in context. So, and each sub-figure just corresponds to one large language model, and the y-axis corresponds to number of passages. So if we have 5 passages, we will just have one golden documents plus 4 negatives retrieved by different retrievers. And the y-axis corresponds to the RAG accuracy or the question answering accuracy. It's worth noting that actually this is a control experiment. So we control the large language model. We control the golden documents presented in context, but we only types of negatives in context. So some negatives are just from random, some are from BM25, some are from contriever, some are from E5. So the red curve here corresponds to we put E5 hard negatives together with the golden documents in context, and the green one corresponds to using contriever to present the hard negatives. Yellow one corresponds to using BM25 to search for hard negatives, and the blue one corresponds to just random negatives. And the negatives documents are selected as the documents which is given a very high retrieval score, but do not present a golden answer inside it. So we can see that actually, if we increase the number of negative passages for all the different like negative settings, the RAG performance will have a decreased pattern. So it means that the more negatives we present in context, the lower the RAG performance is, and the more the LLM is possible to be misled by those negatives. It's also very interesting that if you look at this sub-figure, so if we present E5 hard negatives in context, the performance is the lowest one comparing with if we present BM25 negatives or random negatives. And actually, random negatives have the best performance. And if we refer to the retrieval probability curve, we know that E5 is the strongest retriever, and BM25 and contriever are the second best, and random is just not a very good retriever. It seems like the stronger the retriever is, the harder its retrieved negatives are. So the stronger the retriever is, the more misleading its retrieved hard negatives is. This finding is also can be generalized to Mistral 12 billion instruct model. But the thing is a little different if we use Gemini 1.5 Pro as the large language model in RAG. So if you look at this Gemini 1.5 result, actually, if we input E5 hard negatives, BM25 hard negatives, and contriever hard negatives, we will have a continuous decrease performance, which is the same with Gemma and Mistral. But if we just introduce random negatives, it seems like Gemini 1.5 Pro is quite robust to those random negatives. And even though we increase the number of random negatives, the performance do not decrease, and it seems to be very flat. And we suspect the reason is that when doing Gemini 1.5 Pro training, especially for the long-context modeling, they will introduce this kind of random negatives plus some golden documents training samples. So they are during post-training or pre-training, they have already learned this capability to point out the golden document from random negatives. But still, this kind of capability cannot generalize to golden document plus hard negatives, which is retrieved by different retrievers. The insight here is we know that existing benchmark for evaluating long-context LLMs, such as needle in the haystack or ruler, they just predominantly utilize random negatives. We can see that actually the random negative robustness is not equal to hard negative robustness, which is required in RAG scenario. So this makes us to think that we may need to propose some other more real-world benchmarks to evaluate the long-context capability of different long-context LLMs, especially focus on some real-world scenarios such as RAG. Given that we know that LLMs might be easily misled by hard negatives retrieved by different retrievers, we try to propose some solutions to solve this problem. The first one is called retrieval reordering. So retrieval reordering is actually learned from the idea is borrowed from the loss in the middle phenomenon of larger models. we know that all large language models mainly will focus on the documents or information at the beginning or at the end of the whole input sequence, and will kind of ignore on or less focus on the information present in the middle. So we just borrow this idea and try to use this kind of philosophy to build a bridge between the retriever and the LLM generator. So what we do here is, given a query and a set of retrieval passages, D1, D2, and DK with decreasing relevance scores, usually the vanilla RAG will just input an instruction together with D1, D2, and DK, plus the query queue together, and input them together into a large language model. But we know that LLM will focus more on the beginning, like information, and the information at the end. So it will potentially focus more on D1, D2, and DK minus one DK. And we know that DK minus one and DK, they are just given a very low relevance score, which means that they are potentially negative samples rather than relevant documents. So what we do is, it's a very simple solution. We just reorder the retrieve documents. We put D1 at the beginning, D2 at the end, D3 at the beginning, D4 at the end. So by doing this, we will put the passages with high relevance score at the beginning or at the end. We have the assumption that high relevance score documents is more likely to be the relevant documents. So by doing this, we'll allow the LLM to focus more towards those potentially relevant documents. And we conduct experiment on two datasets, natural question, PopQA, with two retrievers, E5 and BM25, and also with two large language models, Gemma 2 and Mistral. So we can see that this kind of retrieval reordering solution can have a very like significant improved performance compared with original reordering. And this kind of performance improvement is especially very severe when we have a very large number of retrieval passages. You can see here the improvement here the improvement is very large, but if you just have a small number of retrieval documents, the improvement is not that very large. So this makes sense because the more the retrieval passages we present in context, the severe the loss in middle phenomena appears, and also if the more passages we retrieve, the more negatives we have, and if we have retrieval reordering, will potentially alleviate the hard negative issues better. Secondly, we also think about some tuning-based method to improve the large language model for RAG applications. So the first solution we try is called implicitly improving LLM robustness through fine-tuning. So we know that vanilla fine-tuning is like this: give a question, and we will fine-tune the LLM to directly give the answer. But this is not applicable for RAG applications, because during RAG, we not only have a question, but also the retrieve context, and we need to teach the LLM to be robust to the hard negatives retrieved in context, only focus on the relevant documents to give the answer. So what we do here is we propose something like fine-tuning the long-context LLM to be robust to hard negatives. So during for the input prompt, we will not only give the question to the LLM, but also the several retrieved documents, including relevant documents and hard negatives. And given this into the LLM, and we will let the LLM to give an answer to this given question. This is more aligned to how we utilize the LLM for RAG applications. And by doing this, we'll potentially let the LLM to focus, learn to select the relevant documents from all the retrieved documents, and finally answer the question only focus on the relevant documents. And we can see that we conduct experiments on several data sets on three kind of base models: Gemma 2, Mr. Namo, and Gemma 1.0 Pro. And we compare with the original version without any RAG tuning, and we also compare with the model with direct fine-tuning, which is we direct fine-tune the LLM to give an answer for a given question. And we can see that compared with two types of baselines, our proposed robust tuning methods can have the best performance, which means that by doing this implicit tuning, the LLM will have some capability to be kind of robust to the negative retrieving context. However, go back and look at this training samples or training pipeline. Actually, we expect to implicitly let the LLM to learn which documents could be relevant, which document could be irrelevant or hard negatives. And we actually do not teach the LLM to how to select those, how to explicitly select those relevant document out before you give the answer. What we propose next is another training pipeline, which is to enhance relevance identification through reasoning augmentation. So what we do here is when training the LLM, we do not let the LLM to directly give the answer, but first give a reasoning before giving the answer. So the reasoning is like to analyze all the retrieved documents and to select which documents are potentially relevant documents. And based on those like retrieval reasoning, we let the LLM and to have a next step to give a answer. And in our experiments, the reasoning labels are given by, we try both labels given by Gemini 1.5 Pro, which is a large model, and also try the label given by the Llama 3, which is a smaller model. And we find that actually the labels given by different models are quite robust, and we can have improved performance with both the label given by a small LLM or a large LLM. So we show the result here on different data sets, and we try two kind of base models, Gemma 2 and Gemini, and we also show the result of Mistral in our appendix. So we can see that after this this kind of RAG fine-tuning with intermediate reasoning step, we can have a much improved performance compared with the implicit RAG fine-tuning, and also this tool can significantly outperform RAG without any RAG-specific tuning, and also the direct fine-tune baseline. And we would like to show a case of how the implicit RAG fine-tune works and how the RAG fine-tune with reasoning step works. So given a question like this, the ground truth answer is Davy, and we have several, for example, we have 40 retrieved passages. And if we directly use Gemini 2 9 billion to do inference with RAG, it will have this wrong answer. And if we implicitly doing RAG specific fine-tuning, the LLM will just give a very direct answer for this question. It still fails in some cases. But if we fine-tune the LLM with some intermediate reasoning stuff, it will generate something like this. So it will first conduct some very deep analysis of what are the documents which is potentially relevant to answer this question, and then only focus on using this document to answer the question. So finally, we'll have a correct answer based on the very deep analysis of all the retrieved documents. That's it for the method part, and finally, we would like to summarize some takeaways from this paper. The first takeaway is from the analysis part. So we learned that actually increasing the number of retrieved documents in RAG can result in a inverted U performance curve. So it's not like continuous increasing, but increase and then decrease. So this is potentially because of the hard negatives retrieved by the retrievers, and those hard negatives can just mislead the large language model. Thirdly, retrieval precision is not a very accurate matrix to measure the amount of noise or to measure the amount of hard negatives. And lastly, we know that we learned that the stronger the retriever is, the harder its retrieved negatives are, and the stronger retriever is, the more misleading its retrieved negatives are. And from the methodology perspective, we also have three takeaways. The first one is we propose a simple reordering, retrieval reordering technique. And we can see that simple reordered retrieved documents work very well, especially with a larger number of retrieved documents in RAG. And this simple retrieval reordering is very efficient, effective, can be used in a plug-and-play fashion. And even it is retriever agnostic and also large language model agnostic. So it means that if we want to have a very quick solution to adapt long-context LLM to large-scale RAG, we can just try retrieval reordering. And if we have a large number of true documents, this will surely improve the performance, no matter what retriever you use, no matter what large language model you use. And the second solution we propose is implicit RAG-specific large language model tuning. And we find that it can absolutely improve the performance, and it can generalize to some unseen dataset. And lastly, we propose the RAG-specific LLM tuning with intermediate reasoning step, and it will contribute to the best performance. But a bottleneck is sometimes very expensive to get the reasoning labels.
Great session. I love the precision recall metrics and the accuracy. I was thinking though along the lines of, as you increase this number of passages, I imagine the model itself takes some time to think about the right answer, right? So is there any metric on like inference time or from start to end result time that as you vary this number of passages, both with hard negatives and different varying qualities of easy and hard negatives, does that impact when you get to see the answer?
That's true that if we increase the number of retrieved documents, the LM will take much time to do the understanding of the whole context, so whole sequence, and then give the answer. But actually, this efficiency part or time consumption is not related to the the accuracy or the right final accuracy. So it's more like the element takes time to understand it, but it's not because it takes much longer time so that it failed to answer it correctly. So it's more like it's like some kind of long context capability to really understand this, and it will be more likely to be misled by those hard negatives presented in the long time. So finally, it will not be able to answer it correctly. Yeah, thank you for the question. Yeah.
I was wondering what was the performance when you tried on, private models?
We do not try GPT-4 because it's very expensive, but we try Gemini because it's work in Google. Yeah, we show the result here in this figure. You can see that actually for Gemini 1.5 Pro, this inverse U curve do not exist. It can have a kind of consistent improvement if we increase the number of true passages. And I feel like this is because during training, during their LLM post-training or pre-training, they may already seen some samples specific for RAG applications. They may synthetically generate some question together with several true documents, and some of them might be hard negatives. And if the LLM is post-training with such samples, it will have the ability it will be very robust to the RAG applications in the downstream tasks. So, but for those open source LLMs, it still lack the capability to be very robust to the hard negatives. And also, would also like to mention that for Gemini 1.5 Pro, when we are doing the synthetic experiment of hard negatives, if we only put random negative inside, it seems like Gemini 1.5 Pro is quite robust with that. But if we introduce hard negatives retrieved by different retrievers, it seems like the accuracy is still decreasing. So we suspect that when people in Google they are training Gemini 1.5 Pro, maybe they are using random negatives together with the golden documents to let it have the capability to be robust to the negatives. And it's also worth noting that this experiment here and the experiments here are kind of different because for experiments here, for the RAG scenario with increasing number of retrieved passages, we not only introduce more noise, but also more relevant documents. But in the application, in the analysis here, we fix the number of relevant documents to be one, and only increase the number of negatives. So we actually have a decreased performance, but here we have a very consistent improvement or just a flat performance.